So necessity of CMOS analog design. So first point is processing of natural signal. So why we have to what is the requirement of CMOS analog design? So first point is processing of natural signal. So natural signals are in the form of analog form, so we have to process that. For example, the microphone. So output voltage of microphone is in an analog form, that is microvolt to millivolt. So microvolt signal or millivolt signal is not sufficient for processing, so we need amplifier, we need a filter. So this is the analog part. So when you speak in a microphone, that signal which is very low, which is in a microvolt or millivolt, that signal we have to convert in a volt. Second example, a video camera which consists of a photo cell. So output of that photo cell is current and which is very low. It may be few electrons per microsecond. So we have to process that low current. So we need analog CMOS design. Third point, that is a seismographic sensor which is used to measure, which is used to determine earthquake. The output voltage of that seismographic sensor is a microvolt or millivolt. So we have to process on that signal, so we have to use amplifier. So amplifier is an analog part. So see the diagram. This is an analog design. Why we have what is the necessity of CMOS analog design? So we discussed the example of microphone, video camera, seismographic sensor. So we have to design the amplifier. What is the amplifier? Which will increase the amplitude of signal without changing the shape. So input to the amplifier is a millivolt or microvolt signal, and that signal is converted into a voltage. So amplifier will increase the amplitude of the signal. It depends upon the voltage gain of that amplifier. So output voltage is equal to voltage gain multiplied by the input. So amplifier we can design by using NMOS and PMOS, that is a analog design. So output of the amplifier is given to the filter. So filter is again this is analog part. So role of the filter or use of the filter is to remove unwanted signal. So we are using the filters. So to remove the noise signal we can use the filters. There are various types of the filters are available. Depending upon your requirement you can use that filters. So this is analog part. Then you can convert that analog signal into digital signal by using ADC, that is analog to digital converter. So output of analog to digital converter is in a digital form, that is given to the digital signal processor, that is the DSP. So design of ADC for high speed conversion, high speed, high precision and low power dissipation, that is important. So we have to design analog to digital converter with a high speed and high precision and low power dissipation. These are the requirement when you go for designing the analog to digital converter. Second area where we need a analog design, that is a digital communication. See, if this is a lossy cable, you apply the input signal here and you can measure the output at the other end of the lossy cable. If V in is like this square wave, you will get the output, that is the noise signal. So when you send the data to lossy cable, so you will get the noise signal at the output. So attenuation of that signal and distortion of the data through the lossy cable. So this is the problem in digital communication. When you set this input signal, that is a square wave, at the output you will get the attenuated signal with the distortions. So we can use a multi-level signal. So we are using multi-level signal, so reduce the required bandwidth. So this is a 4-level data. So binary data is converted into 4 level. We make the group of 2 binary data to a 1 level. again this another level, this again group of binary third level, and this one is another level. Okay, so in a today's communication system, multi-level signal is required in a digital to analog converter transmitter to produce a multi-level signal from the group binary data. So at the receiver, ADC receiver, to determine which level has been transmitted, so it required high precision of DAC and ADC. So in a communication system, to send the binary data in the form of 4-level data, it required digital to analog converter and analog to digital converter with a good precision. So we have to design a analog CMOS design. Next area for analog design is disk drive electronics. So see the data. So we store this data on a computer hard disk magnetically in a binary form, and when you try to read that data by magnetic head and convert into electrical signal, so received data is like this. Okay, so this is a stored data and this is a received data. So you store the data magnetically on computer hard disk in a binary form, and when data is read by the magnetic head and it converted into electrical signal, so this is a received data and this one is a stored data. So you receive the noise signal, so you require the filter. So filter will remove the noise signal, unwanted part. So you have to design the filter such that you have to consider the speed of the computer. Next area for analog design is a wireless receiver. So signal pickup by antenna of RF receiver, for example mobile phone. So amplitude of that signal is very low, it is a microvolt, and the center frequency is 1 gigahertz. So you have to design the amplifier such that it should increase the amplitude of the signal, so which will convert the microvolt signal into volt. But you have at the same time you have to consider the central frequency, that is 1 gigahertz, which is very high. So analog amplifier design, and you have to consider the frequency response for that amplifier. At that time you have to consider the frequency, that is 1 gigahertz, and we can say this is a central frequency. Next area for analog design, that is a optical receiver. Now see, for the transmission of high speed data over the long distance, cables are not useful because they have limited bandwidth and the attenuation of the signal. So when you are transmitting the high speed data over the long distance, you will not go for cables because it having some drawback, that is limited bandwidth and attenuation. So this is a transmitter, laser diode, optical fiber, receiver, and photo diode. So we send the data in the form of light. So which light will be fall on photodiode. So at the receiver end, the light signal is converted to an electrical current by the photodiode. So this receiver must process a low level signal with a high speed and low noise. So that is the analog design. So this light signal is converted into electric current by the photodiode. So this receiver must process that low level signal with a high speed and low noise. Next area, sensors. So we already discussed that video camera, which consists of array of the photodiode that will convert an image to the current. Ultrasound system use acoustic sensor to generate a voltage which is proportional to the amplitude of ultrasound waveform. So in this case we need the amplification and filtering. Again we need analog to digital conversion. So design of this analog part is very important in a ultrasound system. Next area, microprocessor and memory. Distribution and timing of the data and clock across a large chip is an analog form. So signal and power interconnection on that large chip is required a good understanding of analog design. Now see, the microprocessor of memory having a large chip, and this complication, there is a complicated interconnection. So you should having a good knowledge of that interconnection. So you should know the analog design. Now why we go for the CMOS? Now first reason is CMOS gate will dissipate the power only during the switching. CMOS gate terminal will dissipate the power during the switching. So dimension of CMOS devices, MOS devices can easily scale down. We can reduce the size of MOSFET, that is W, width and length of a MOSFET devices easily. So low fabrication cost for the CMOS, and we can place analog as well as digital circuit on a same chip. So why we go for the CMOS? The first reason is that CMOS gate will dissipate the power only during the switching, and the dimension of the MOS devices are easily scaled down. A low fabrication cost, we can place analog and digital circuit on a same chip. Next, we will discuss the MOSFET structure. So this is for NMOS. So it is fabricated on P-type substrate. So whenever you say NMOS, the substrate is opposite. NMOS, that is N-channel metal oxide semiconductor transistor. It consists of 3 terminals: source, gate and drain. So it is fabricated on P-type of substrate. Source is made up by N-type of semiconductor material. Drain is made up of N-type of source semiconductor material. Gate terminal is isolated from the channel by silicon dioxide layer. NMOS is fabricated on P-type substrate. Source, which is made up of N-type of semiconductor material. Drain, which is made up of N-type of semiconductor material. So N plus indicate that more number of electrons are available, so it is heavily doped. So electrons are moving from source to drain through this region, that we can say the channel. So initially this MOSFET is off condition. When we apply a positive voltage on gate, so electrons are entering in this region and they are trying to move towards the drain, and the drain current start to flow in a MOSFET. So source is a supplier which will provide the electrons, and drain is a collector which will collect that electrons. So electrons are moving from source to drain when you apply the proper voltage on a gate and a drain terminal. So for the NMOS, we apply the positive voltage on a gate and we connect a drain terminal to the positive terminal of the supply. So for the minimum voltage required to turn on the MOSFET, that is a VTH or threshold voltage. So when you apply a minimum voltage on a gate, so channel is created and electrons are moving from source to drain, and drain current start to flow in a MOSFET. So when you increase voltage on a gate, so it will increase more number of electrons are moving from source to drain. So drain current ID will increase accordingly. So this is a voltage control device, because voltage on gate control the movement of electron from source to drain, and it control the drain current. So it is a voltage control device. Output current is controlled by voltage on gate and source. So for the PMOS, opposite type of substrate, that is N-type substrate. Source is made up of P-type of semiconductor material. Drain is made up of P-type of semiconductor material. P plus means more number of holes are available, so it is heavily doped. So this is a structure of PMOS devices. Source, gate and drain terminal. Gate is isolated from the channel by using silicon dioxide layer. Initially channel is absent because MOSFET is off. We have to apply the proper voltage on gate, that is negative, and drain terminal is connected to negative terminal of a supply. So for a CMOS, NMOS and PMOS device are fabricated on a same wafer, that means same substrate. For this reason, one device can be placed in a local substrate that we can say well. So CMOS process, the PMOS device is fabricated in a N well. So N well must be connected to the potential such that source drain junction of PMOS transistor must remain a reverse bias under all the condition. So this is a PMOS device fabricated in local substrate, that is N well. So P plus, that is a source terminal, P plus, that is a drain terminal, that is a P type of semiconductor material. Gate is isolated from the channel by silicon dioxide layer, and this is a NMOS which is fabricated in P type of substrate. So for the NMOS, source is made up of N type of semiconductor material, drain is made up of N type of semiconductor material. So this is a diagram of CMOS which is fabricated by using NMOS and PMOS. Now see the symbol of MOS. This is a symbol for NMOS, gate, terminal, drain and source. If you see this arrangement, so gate, terminal and channel is one of the component like capacitor. So this is a capacitor. So this arrow will indicate the current direction. So this is a symbol for NMOS, and for the PMOS, see the arrow, opposite arrow which is a inward arrow on a source terminal. This is another way to draw the NMOS and PMOS. Next, that is a transistor IV characteristics, that is current and voltage characteristics. So we will discuss for NMOS. So this is the diagram of NMOS. So it is fabricated on P type of substrate. We have to apply the proper voltage on a gate. So we gate terminal is connected to positive terminal of the supply. This is a body terminal which is grounded. Drain is connected to a positive voltage of the battery terminal. So basically, when you apply the voltage on a gate, this is positive voltage on a gate, so it will create a negative ions in this channel region. So these are the negative ions. So when you apply the positive voltage on a gate, it will create a negative ions in a channel region, because if one of the plate of the capacitor is positively charged, other plate is negatively charged. So these are the negative ions. So the p-type substrate which contain the holes, and these holes in this region are replaced by the negatively charged ion. So this is a formation of depletion region. This is the formation of depletion region. Now when you apply the voltage on gate, that is positive, so electrons from source terminal will try to move towards the drain. So they will enter in this region and channel is created. So whenever voltage on gate is equal to VTH, that is the minimum threshold voltage required to turn on the MOSFET, so channel is created and electrons are moving from source to drain. So when you increase this voltage on gate, so more number of electrons are trying to move from source to drain, and this depletion region charges are move downwards. So electrons are moving from source to drain, and drain current start to flow in a MOSFET. So if you see this, initially here holes are present because this is a p-type substrate, and these holes are replaced with the electrons because by applying the proper voltage on gate and drain terminal. So this formation of this is a inversion layer. So holes are replaced with the electrons, so this is the inversion layer. So equation for VTH is equal to phi ms plus 2 phi f plus q depth divided by COX. So phi ms is a difference between work function of polysilicon gate and silicon substrate. Phi f, that is a kT by q ln of n substrate divided by ni. So q is the charge on the electrons, n substrate is doping concentration of substrate, q depth, that is a charge in a depletion region, COX, that is a gate oxide capacitance per unit area, COX. Ni is the intrinsic concentration of silicon. Now see this graph, we will see the equation of drain current in a linear region and saturation region. So this is the equation for linear region. Drain current is equal to mobility of electrons, gate oxide capacitance, width and length of transistor, VGS minus VTH, voltage of gate and source minus threshold voltage, multiply by VDS, that is a drain to source volt, minus 1 by 2 VDS square. So this is the equation A. So ID is equal to mu n COX W by L multiply by VGS minus VTH into VDS minus 1 by 2 VDS square. So this is the mobility of electrons. So figure, we can draw the graph of drain current ID versus VDS. So this is a parabolic equation given by the equation A. So this is a parabola given by the equation A. We discuss the triad region. So you will get the peak value when VDS is equal to VGS minus VTH. So that is the saturation region. Okay, you get the maximum value of the current when the drain to source voltage is equal to VGS minus VTH. So saturation region ID equation is ID max is equal to, that is the maximum drain current, is equal to 1 by 2 mu n COX W by L VGS minus VTH bracket square. So when you put this VDS is equal to VGS minus VTH, you will get the equation B, that is the ID is equal to 1 by 2 mu n COX W by L VGS minus VTH brackets square. So if in equation A, if this equation A, we will discuss about this deep triad region. So this VDS is very small as compared to 2 times of VGS minus VTH. So ID is equal to mu n COX W by L VGS minus VTH into VDS. So this is the ID. We neglect this term. So equation C, the drain current is equal to mu n COX W by L VGS minus VTH into VDS. So if you observe this equation, drain current is a linear function of VDS. So this is the region. In a deep triad region, MOSFET act as a resistor because drain current ID is a linear function of VDS, and that is given by VDS by ID is equal to 1 upon mu n C ox W by L VGS minus VTH. So R on is equal to 1 upon mu n C ox W by L VGS minus VTH. So in a deep triode region, transistor can be act as a linear resistance, and that is given by this equation. R on is equal to 1 upon mu n C ox W by L VGS minus VTH. So a transistor is replaced with a resistance between source to drain, and whose value is controlled by the VGS.